Okay, let's unpack this. In the sprawling, complex world of modern cloud architecture, where resources spin up and down faster than you can pour a cup of coffee, security can often feel like you're trying to herd cats,
Hey, it really can.
but it shouldn't. The foundational truth in Google Cloud Platform is that the very first line of defense, the bedrock of any secure environment, starts at the network level, specifically with granular traffic control.
That's absolutely right. Today, we are strapping in for a deep dive into the foundational, yet surprisingly tricky mechanics of VPC firewall rules in Google Cloud Platform.
And this isn't just a casual overview.
No, not at all. And let's be clear about who this is for. This is a curriculum-level, high-stakes analysis specifically curated for you, the learner preparing for the GCP Professional Cloud Architect, the PCA exam.
Our mission today goes far beyond basic configuration. Anyone can click Allow All and open a port. We are digging into the hidden gotchas, the strong security postures, and the organizational governance principles that are truly the difference between an administrator who can manage a project and an architect who can design and secure an entire enterprise fleet at scale.
And that's the point. If you miss these nuances, the exam will definitely catch you.
Absolutely.
Our source material is perfect for this endeavor. It synthesizes hands-on configuration wisdom with crucial architect's notes and those sneaky exam triggers.
No exam triggers.
Exactly. This offers a direct, efficient shortcut to internalizing precedence rules, policy mandates, and, most importantly, the high-level security mindset Google expects of its certified architects.
So it's about thinking like an architect.
It's all about thinking like an architect. If you can speak the language of governance and hierarchy and firewall rules, your network security posture is sound.
Let's start at the beginning, but with that necessary PCA angle. What exactly are these firewall rules doing, and where is their domain within Google Cloud?
Okay, so at their most basic, GCP firewall rules are the gatekeepers. They are the mechanism that controls all IP traffic flowing to and from your VM instances within a virtual private cloud, your VPC network.
So they live inside the VPC.
They do. They operate in the layer 4 transport layer, controlling protocols and ports. Now, the crucial architectural fact to nail down immediately is one of scope. Each VPC network has its own firewall.
That concept of independent scope is really important. If I have Project A with VPC Alpha and Project B with VPC Beta, the firewall policies in Alpha have absolutely zero bearing on the traffic moving through Beta unless I explicitly connect them.
Exactly. They operate entirely independently of each other. This independence is fundamental when you think about security isolation and network segmentation across different business units or environments like development versus production.
They're like walled gardens.
They are. They are isolated worlds unless you use complex connectivity services like VTC peering or cloud VPNs to link them. And even then, the rules govern the traffic entering or leaving that local VPC endpoint.
Let's move to the most important characteristic of these firewalls, the concept that often confuses people used to older networking stacks: statefulness. Can you define stateful behavior in this context and explain why it saves us a tremendous amount of configuration work?
Absolutely. This is a game changer. The rules are fundamentally stateful. This means the firewall tracks the connection established between two endpoints.
It has a memory.
It has a memory. Let's use the classic web server example. You define an ingress rule, that's incoming traffic, to allow an HTTP connection on port 80 from the internet to your web server VM.
So the inbound request is allowed.
Once that initial connection is established, the firewall remembers it. The data that flows back, the actual web page content leaving the VM and going back to the user, is technically egress traffic.
Right, outbound.
But because the firewall is stateful, the return egress traffic for that specific established connection is implicitly allowed. You don't need a separate corresponding egress rule to permit the response.
So it's not just a pass-fail check on a packet. It's an intelligent tracking system of the entire session.
That's it.
It's like a conversation. I allowed you to call me, so I implicitly allow myself to reply to your initial statement.
Precisely. And this is symmetrical. It works the other way if you initiate the connection.
Okay.
If you have an egress rule that allows your VM to start a connection, say calling an external API endpoint on port 443, the corresponding return ingress traffic carrying the API's response is also implicitly allowed.
That makes so much sense.
Statefulness is what allows modern firewalling to be so performant and efficient, preventing the need for mirrored manual rules for every single flow.
Now we get to the core knowledge required for the PCA exam. The implicit traps.
Mm.
These are mandatory facts
Yeah.
because they define the default security posture of every VPC network, and they are the #1 cause of initial deployment headaches.
Oh, absolutely. This is where the architect steps in. Every VPC network starts with 2 non-configurable foundational implicit rules. The first and most comforting is the implicit deny ingress. All incoming traffic is blocked unless you explicitly create an allow rule to permit it. This is a very strong, secure posture by default.
Secure by default. I like that.
Exactly. Nothing can talk to your VMs from the outside world or even from other private subnets within the VPC until you specifically open the door.
A great security default. Now for the trap, what's the flip side?
The flip side is the implicit allow egress. By default, all outgoing traffic is allowed to any destination unless you explicitly create a deny rule to block it.
Oh,
This is the hidden vulnerability because while the front door ingress is locked, the back door egress is wide open.
that example perfectly frames the default position. I get it. But architecturally, why does Google choose this specific asymmetric security stance? Why not just deny everything by default, both ways?
That's a deep architectural question that speaks to operational utility. I mean, imagine if every new VM couldn't even fetch its initial configuration, contact NTP services for time synchronization, or download essential boot images from Google's internal service endpoint.
You'd be stuck before you even started.
You'd spend the first 15 minutes of every deployment writing explicit allow egress rules just to make the machine functional. Google prioritizes operational simplicity combined with that strong perimeter defense.
So they're saying, we'll protect you from the outside world by default, but we trust that the code you run internally knows where it needs to go unless you tell us otherwise.
That's a great way to put it.
That makes sense for speed, but that implicit allow egress is the architect's first big responsibility, isn't it? It's a huge potential vulnerability.
It is the single biggest governance failure point. The security architect's mantra should be, thou shalt not trust the implicit allow egress.
I'm writing that down.
That's where a rogue process or even a simple misconfiguration can quietly initiate data exfiltration to an external server on port 443, which is often implicitly allowed, and you won't realize it until the data is gone. That's why overriding that default is a core responsibility.
This leads us directly to that classic PCA exam, a troubleshooting scenario that tests these interaction mechanics.
The scenario goes like this. You deploy a new Linux VM. It successfully downloads operating system updates from the public repositories, meaning it is initiating outbound connections.
Okay, so it can talk out.
Exactly. However, when you try to use the SSH client from your jump box to connect to it, the connection times out. Why?
The tempting answer is always to blame the update service, or maybe a network glitch. But the true root cause lies with the default firewall rules.
Precisely. The instance successfully downloads updates because outbound traffic is permitted by the implicit allow egress rule. But you cannot SSH to it because SSH requires incoming ingress traffic, which is blocked by the implicit deny ingress rule.
So simple when you break it down.
It is. You need to create an explicit ingress rule for TCP port 22. This distinction mastering the interaction of these two defaults is fundamental before we move on to crafting custom rules.
Moving beyond the defaults, we need to understand how to build a precise, custom rule that targets exactly the traffic we want. Let's meticulously break down the anatomy of a VPC firewall rule. Our source material outlines 6 critical components.
These 6 components are the only levers you have, and mastering their interaction is essential. First up is direction.
In or out. Simple enough.
Ingress for traffic flowing into the VM, or egress for traffic flowing out of the VM. Second, and this is absolutely critical for the exam, is priority. It's a number from 0 to 65535.
And lower is better.
Lower number equals higher priority. A rule at priority 100 is checked and enforced before a rule at priority 1000. It's a common stumbling block.
Got it. What's third?
Third is the action. Simple but irreversible. Allow or deny the matching traffic. Fourth is targets. Who is affected by this rule?
Okay, so this is where you specify which VMs the rule applies to.
Exactly. You can select all instances in the VPC or specific subsets based on network tags or the service account attached to the VM instance. This dictates the recipient of the rule.
And what about the other side of the connection?
That's number 5. Source or destination filters. This dictates the origin or endpoint. For ingress, this is the source where the traffic originates from. For egress, this is the destination where the traffic is going.
And you can filter that by IP ranges or also by tags and service accounts.
You can, which we'll get into in a big way. And finally, number 6 is protocols and ports, the granularity layer, TCP, UDP, ICMP, or specific port numbers.
Like TCP.22 for SSH, UDP.53 for DNS, or TCP.80, TCP.443 for standard web traffic.
You've got it. Combining those 6 levers correctly is the entire ballgame.
Let's look at the absolute most common administrative task.
Yeah.
Securing management access.
Right. Ingress scenario 1. Basic SSH access. If we were just performing a basic admin task, our goal would be to allow SSH on port 22 only from a trusted administrator IP range.
Like the corporate office VPN, say 203.113.024.
Exactly. The configuration is straightforward. Direction, ingress, action, allow. Protocol.tcp.22. Source filter. That specific trusted CIDR block. And for the target, let's say all instances.
That is a functionally correct, valid rule. It works. It restricts access to known IP addresses, relying on the implicit deny to block the rest of the world.
It does work.
But here is the major architectural pivot that the PCA exam forces you to make. The source material specifically highlighted the architect's preferred solution, Identity-Aware Proxy, IAP.
This shift is essential, and it's one of those major distinction points. While the firewall rule approach works, it still exposes port 22, even if only to a limited set of IP addresses. It's a public exposure.
A surface area for attack.
A huge one. The best security posture in Google Cloud is to leverage Identity-Aware Proxy, which flips the security model from network-centric to identity-centric.
IAP is a game changer because it doesn't rely on where you are connecting from. It relies on who you are, managed through IAM roles.
Exactly. IAP allows you to tunnel TCP traffic, including SSH, through Google's global, highly protected infrastructure. You authenticate using your Google identity and IAM permissions.
Which means you can access your VMs securely without exposing port 22 to the public internet at all. The traffic never needs to hit a public IP assigned to the VM itself.
Correct. It's a much, much stronger posture.
But even when using IAP, the documentation is clear. You still need one very specific firewall rule to enable the tunneling mechanism to talk to the backend VM. What's the detail the architect must memorize?
Okay, this is a key exam fact. You must create an ingress allow rule for TCP port 22, but the source range has to be restricted exclusively to Google's managed IAP health check and tunneling range. That CIDR block is 35.235.241 on 020.
35.235.240.0/20.
That's the one. If you see a question about secure SSH access that specifically restricts public exposure and leverages IAM, this specific CIDR range combined with the use of IAP is the required architectural answer. It minimizes the surface area of attack significantly.
That is a critical detail. Memorize that 35.235.240.020. Moving past management, let's look at internal application communication, specifically again to scenario 2, internal application tier communication. This is a common multi-tier deployment.
It is. Let's define the scenario. We have a web server tier running on port 80 and an application server tier running on a dedicated port, say 8080.
A classic setup.
The web servers need to initiate connections to the application servers, but no other internal machine like a database server or a monitoring jump box should be able to access the app server on 8080.
So least privilege, even inside the VPC.
Precisely. Since both are inside the same VPC, how do we enforce this least privilege principle?
We use the filtering mechanisms we just discussed, particularly tags.
Correct. We configure an ingress rule with direction, ingress, action, allow, protocols.tcp.8080. Crucially, we set the target to instances tagged app server, that's the recipient.
Okay.
And we set the source filter to instances with the tag web server, the only authorized initiator.
That tag-based filtering seems highly scalable. Spin up 100 new web servers. As long as they carry that web server tag, they instantly gain access to the application tier without any rule modification.
It is scalable, and it's functional. That reliance on tags, as you just articulated, leads us directly into our next section, which is a major point of confusion and a frequent source of failure on the PCA exam. It's the difference between convenient configuration and strong security governance.
This shift is vital. We've established that filtering traffic by source identity or characteristic is necessary, but the architectural question is, which mechanism provides a stronger, more verifiable security guarantee? Tags or service accounts?
This is the inflection point, where configuration detail meets enterprise security policy. Let's dissect the limitations of tags first.
As we mentioned, tags are simple. They are user-defined string labels, web server, staging, database. They are easy to assign, easy to use in firewall rules, and easy to read.
And that simplicity hides a severe security risk. The critical vulnerability is that anyone with the compute.instance admin IAM role, which is a relatively common permission granted to development teams for basic operational tasks, can change the tags on a VM instance.
Okay, so if I'm an attacker or a disgruntled employee who has compromised a low-privilege VM, I can look at the firewall rules, see that the app tier allows traffic from web server tags, and just apply that tag to my rogue instance.
Precisely. You simply tag the compromised machine as web server and immediately bypass the firewall rule designed to protect the application tier.
Wow.
The firewall sees the tag and boom, access granted. Because tags are just labels, they are a weak source of security identity when strict governance is required.
That highlights the failure. Tags are network identifiers, not security identities. So how do service accounts and SAs solve this problem?
Service accounts are fundamentally different. They are not mere labels. They represent a cryptographic identity attached to the VM instance. They are the actual primary identity that the VM uses to interact with other Google Cloud services, and they are governed entirely by the IAM framework.
So how does that translate into security strength that tags don't possess?
Well, the strength comes from the elevated control plane required to manipulate that identity. Changing the service account attached to a running VM requires a specific, highly elevated IAM privilege.
Which one?
Specifically, the IAM.serviceaccounts.actDays permission, which is often called the service account user role. This permission is typically locked down and restricted to senior security or cloud administration teams.
That's the critical difference. If a rogue administrator tries to impersonate a trusted web server, they can easily change a tag using routine admin privileges.
But they cannot easily swap the underlying cryptographic identity, the service account, without having those highly restricted ACTAs permissions.
So the IAM framework protects the integrity of the firewall rule.
That is the core architectural takeaway. And this brings us to the firm verdict for your exam strategy, which is one of our most frequently tested concepts.
Okay, let's hear it.
For any question demanding the strongest security requirements, the highest integrity posture, or scenarios where least privilege must be strictly enforced, always choose filtering traffic by source service account over source tags.
Always.
Always. Using service accounts for filtering moves the security decision from a mutable network label to an immutable, cryptographically verified IAM identity.
That is fantastic context. It's the difference between asking for someone's name, which is a tag, versus asking for their government-issued ID, which is a service account. You rely on the latter for high-trust environments.
That's a perfect analogy.
We've spent necessary time locking down the front door, ingress fighting the implicit deny. But now, let's pivot to egress outgoing traffic, where we must fight against that massive security hole of the implicit allow egress rule.
Controlling egress is essential, yet often the last thing architects think about until they have a security incident. The primary purpose is strictly govern data integrity.
Preventing data exfiltration.
Exactly. Preventing unauthorized data exfiltration and limiting outbound connections to only necessary services, thus shrinking the VM's attack surface. If you fail to override that default implicit allow egress, you failed the security architecture mandate.
Overriding the implicit allow, however, isn't simple. If I slap down a deny all egress rule right away, I break all legitimate operational processes, DNS, updates, API calls.
You'd break everything.
We need careful orchestration, specifically around priority, to make sure the essential traffic gets out first.
This is where the sequencing becomes critical. Let's walk through egress scenario 1. Restricting outbound internet access. This is the definitive governance pattern.
Define the requirements for us.
Okay. We have application servers that need external access only to a very specific approved third-party API. Let's use the range 198.51.10.029 on port 443, and they must also perform DNS lookups on port 53.
And everything else is blocked.
All other traffic to the internet must be blocked. This requires a meticulously sequenced 3-rule sequence. Remember the rule. Specific allow rules must be processed at a higher priority, so a lower number than the general deny rule.
Like rule number 1.
Rule 1 is allow API, priority 100. This is the highest priority exception. Direction, egress, action, target app server instances, destination 198.51.100.0.029. Protocol.tcp.443. We assign it priority 100. This traffic is allowed, and the evaluation stops.
Makes sense. Next, the necessary utility traffic. DNS. This is tricky because DNS lookups go everywhere.
Right, so rule 2 is allow DNS, priority 110, direction, egress, action, allow, target.app server, destination. .0.0.00, which allows any destination, which is required for general DNS lookup, protocol.udp.53. We give it priority 110. It is processed after the highly specific API call rule, but still before the denial.
Yeah, we execute the architectural mandate.
Yeah.
Kill the implicit allow.
Now we bring down the hammer. Rule 3 is deny all else. Priority 120, direction, egress, action, deny, target.appserver, destination, 0.0.000, everywhere.
Yeah.
Protocols, all protocols, priority 120.
The logic is now undeniably clear. The firewall checks 100, then 110. If the packet matches either of those, it gets out.
And evaluation stops.
If it doesn't match the specific allows, it then hits 120, the blanket deny, and stops dead. The implicit allow egress rule, which exists at the lowest possible precedence, is never reached.
That sequencing is the bedrock of compliance and security design. If you put that deny rule at priority 50, you deny everything, and the entire application fails. Craft the exceptions first with a tight priority band, and then enforce the general denial as the absolute safety net.
That tight control is vital for external connectivity. Let's pivot to securing internal east-west traffic, specifically connections to Google Managed Services, which often use private service access networks. Egress scenario 2. Connecting to managed services, like Cloud SQL.
Good one. Let's say our application VMs need to connect to a private Cloud SQL instance, perhaps a database endpoint running MySQL on port 3306. The traffic is internal to the Google Cloud Network, staying within Google's private backbone, but it still originates as outbound traffic from your VM.
And since we just blocked all general egress with our priority 120 rule, we need an explicit allowance for this internal path.
Exactly. We configure a new egress allow rule, likely at priority 50 or 60, to ensure it's processed quickly. Target.appserver. The critical filtering mechanism here is the destination filter,
Which would be?
which must be the specific IP range dedicated to the Cloud SQL Private Service Access Network. This is often a range like 10.1 to 0.028 that you reserve for managed service access. And protocols, of course, TCP to 33806.
The architectural beauty here is the principle of least privilege in action. That egress rule doesn't allow the app server to talk to any other internal machine, nor does it allow talking to the internet.
No.
It allows connectivity only to the secure database endpoint within the tightly controlled private access range.
It reinforces the point. Egress rules are not just about preventing outside threats. They are equally vital for fine-tuning internal east-west traffic flows, especially to highly sensitive managed services. It guarantees that even compromised application code can't pivot to other sensitive internal services.
We've mastered the mechanics of a single rule, but the job of the professional cloud architect isn't to manage rules one by one. It's about governance. The real challenge is managing security across 100 VPCs spread across 20 projects.
Or ensuring compliance when local developers have permissions to modify rules locally.
Exactly. How do you scale this?
This moves us into the realm of enterprise control, and the solution is hierarchical firewall policies, HFP. This mechanism solves the compliance and scale problem instantly.
Walk us through the concept of HFP. How does it fit into the Google Cloud Resource hierarchy?
Right. HFP allows you to define policies not at the VPC or project level, but at the organization level or the folder level, which sit higher up in the resource structure.
So it's a top-down approach.
It's the ultimate top-down approach. Think of this as the corporate security mandate written in stone.
And its power lies in enforcement.
Yes. These policies are inherited by all VPCs underneath that point in the hierarchy. If you define a rule at the organization level, every single project, every folder, and every VPC in your entire GCP estate instantly inherits and enforces that rule.
That's powerful.
The scale and the non-negotiable nature of HFP are what make it architecturally necessary for large organizations.
This is a loud siren for an exam trigger. If a scenario mentions centralized control across multiple projects, or ensuring compliance for all current and future VPCs, or most crucially, local admins cannot override, you're being directed straight to hierarchical firewall policies.
100%. Let's make the precedents crystal clear. Imagine a corporate mandate to allow only traffic from the internal corporate VPN range, say source, 172.16.0.016, to access any internal service on port 8080.
Okay.
You implement this as an HFP. That rule applies to every VPC instantly. If a local developer then tries to create a local VPC rule to deny all traffic on port 8080, the HFP rule, due to its place in the hierarchy, is evaluated first and it wins. The developer's local denial is ignored.
So the organization policy takes precedence, period.
Hierarchy always wins. That's the core principle that makes HFP the only governance mechanism for compliance.
Now, shifting from policy enforcement to detection and diagnosis, the second critical element for architectural maturity is firewall rules logging.
Configuration without observability is a security blind spot. Logging can be enabled on individual firewall rules.
And what do these logs actually capture?
They capture vital metadata.
Right.
The source and destination IP, the protocol and port, the action taken allow or deny, and most importantly, the specific rule that was matched and caused that action.
This sounds critical not just for finding bugs, but for satisfying regulators.
Absolutely. The primary architectural use cases are twofold. First, auditing and compliance. Regulatory frameworks like PCI DSS or HIPAA often demand a verifiable, auditable trail showing exactly which traffic was allowed or dropped. Logging provides that evidence.
And the second use case.
Second is troubleshooting. It allows you to definitively determine exactly why a packet is dropping or which unexpected rule is intercepting traffic before it hits the intended target rule.
So the exam trigger here is straightforward. If a scenario asks you to verify if traffic is being blocked by a specific rule, or needs you to analyze traffic patterns to find an unexpected block or an attempted unauthorized connection, the required architectural action is enabling firewall rule logging.
It is the difference between guessing what the firewall is doing and actually knowing.
Finally, we must synthesize everything, the implicit rules, the HFP, the VPC rules, and the priority numbers, into one definitive order of evaluation. This is the moment a packet hits the VPC boundary and the entire precedence mechanism kicks in.
This specific three-step sequence is non-negotiable, and you need to internalize it. Highest precedence is number 1. Hierarchical Firewall Policies, HFP.
Top of the chain.
They are evaluated first, starting at the organization level and moving down through any intervening folders to the project level. Crucially, if an HFP rule is matched and its action is allow or deny.
Meaning it's enforced, not set to go to next.
Right. If it's enforced, the evaluation process stops immediately.
Okay, so the packet never even sees the local rules. But if the packet survives the HFP gauntlet, or if the HFP explicitly directs it to the next layer using the go to next action.
Then we move to step 2, VPC firewall rules. These are the rules we configured locally within the VPC network.
And these are sorted by priority.
These are strictly sorted and evaluated by their priority number lowest integer first. Again, if a rule is matched, the evaluation stops.
And only if no custom HFP or local VPC rule has matched the traffic.
Then, and only then, do we hit step 3. The implied rules. This is the lowest precedence layer, which defaults to implicit deny ingress and implicit allow egress.
So that hierarchy confirms that any explicit rule, whether organizational or local, will always override the implicit defaults.
Always.
That order of evaluation is the blueprint. Let's immediately apply it to real-world scenarios, particularly focusing on how priority numbers interact with allow and deny actions. Let's reiterate the fundamental rule. Lower integer equals more.
Higher priority.
We need to avoid the simple arithmetic mistake that traps so many people. Practice question analysis 1 focuses on priority precedence in that critical egress setup we discussed earlier.
Here's the scenario. We deployed 2 egress rules. Rule alpha is deny all egress, priority 900. Rule beta is allow egress to a specific API range, priority 1000.
Okay.
The application team reports that traffic to that specific allowed API range is being blocked. Why?
The mistake is obvious once you understand precedence. The system evaluates rule alpha, the deny rule at priority 900, first because 900 is lower than 1000.
It sees deny.
It sees deny. And because firewall evaluation stops upon the first match, the system executes the deny, and rule beta at priority 1000, the specific allow exception, is never reached. So even though the architect intended to allow the traffic specifically, the poorly prioritized general denial killed the packet before the exception could be processed.
Exactly. To fix this, the specific allow rule must be prioritized higher. It needs an integer value lower than 900, say, priority 899 or 50.
So the exception has to come first.
The exception must be evaluated first. This confirms that sequencing your exceptions correctly is as important as the rule content itself.
Let's tackle the most complex exam scenario, the one that tests hierarchy, governance, and override potential. Hierarchy enforcement.
This question combines everything. The organization has a strict corporate policy. No public SSH access is allowed. A blanket deny on port 22 from 0.0.0.00.
Makes sense.
But a local development team, seeking convenience, created a local VPC rule allowing exactly that. 0.0.000 on port 22, violating corporate policy.
A classic problem.
So the architect needs a solution that enforces the block across all current and future projects, and local administrators must not be able to override it.
Let's analyze the attractive but incorrect traps first. One suggested solution was to simply create a local VPC firewall rule with priority 0 to deny ingress on port 22. Why does that fail the architectural requirement?
It fails on the governance requirement. While priority 0 is the highest local VPC priority, the local project administrator, the very person causing the issue, has permission to modify, disable, or delete that rule instantly.
It's not permanent.
It might be a quick fix for today, but it is not a preventative organizational control that guarantees future compliance across the entire enterprise. It doesn't enforce the mandate.
Another tricky option involves hierarchical firewall policy but misconfigured. Option B suggested implementing an HFP at the organization level with a deny rule on port 22, but setting the enforcement action to go to next. Why is go to next the fatal flaw here?
Go test is the mechanism for delegation. When the packet matches the HFP rule, the policy says, I see this traffic, but I'm going to pass the decision down to the next level of the hierarchy.
And the next level is?
The next level includes the developer's local VPC rule that allows port 22. So the traffic proceeds to that local rule and is ultimately allowed. The org-level policy failed to enforce the block because the architect told it to defer.
That leaves the definitive architectural answer.
The correct answer. Implement a hierarchical firewall policy at the organization level with a deny rule on port 22 using the explicit deny action which is enforced. This is the definitive preventative control.
Why?
Because HFPs are evaluated before all VPC rules. The org-level deny blocks the traffic instantly at the network boundary, and because it is managed at the org level, local project administrators cannot override or delete it. Hierarchy wins, and compliance is enforced at scale.
Let's quickly circle back to our security posture discussion with the second practice question, focusing on internal traffic between web and app tiers. We need the configuration that provides the strongest security posture given the known risk that instance administrators can easily edit tags.
Right. The options were filtering by tags, filtering by service accounts, or filtering by IP subnets. The source provided the clear architectural imperative. Option B, configuring an ingress allow rule filtered by source service account and target service account.
And the ultimate reason, which bears repeating for the exam, is the linkage to the IAM framework.
Precisely. Filtering by service account is the strongest security measure because it leverages the IAM framework, requiring those highly elevated permissions, im.serviceaccounts.actAs, to change the VM's identity.
Well, tags are easy to change.
Tags are easily changed by general instance admins, making filtering by tags fundamentally insecure for high trust requirements. Subnet filtering is too broad. It allows any compromised machine in that network range to gain access.
So the hierarchy of trust is clear.
Absolutely. When the exam asks for strongest security, you must think identity, which is the service account, over location, the subnet, and identity over easily mutable labels, which are the tags. We have established the 4 critical levers you need to pull successfully, not just for passing a test, but for designing real-world secure environments. Let's review them one last time.
Let's do it.
First, hierarchy wins organization and folder policies are your central enforcement point and override local VPC rules.
Got it.
Second, logging matters. You need logs enabled on key rules for compliance, auditing, and accurately diagnosing dropped packets. Third, the numbers game low or integer equals higher priority, which is vital for ensuring your specific exceptions, the allowers, are processed before your general security nets, the DNS.
And finally, the big one.
And fourth, identity over string service accounts provide a cryptographically safer, governance-backed method for filtering traffic than easily mutable tags.
If you leave this deep dive with those 4 concepts fully locked in, you have not just prepared for a high-stakes certification exam, you have internalized a high-value mental model for designing cloud networks that are secure by default, manageable at scale, and easily auditable.
That's the goal.
That is the true difference between an administrator and a certified architect.
That high-level thinking is what we aimed for today. Since hierarchical firewall policies provide this unprecedented control across all projects and folders, consider this as a final provocative thought.
Okay.
How might an architect use a highly prioritized, subtle, allow rule within an HFP to secretly create a centralized monitoring capability like allowing specific outbound ports to only a centralized security monitoring VPC that no local project administrator could ever disable or modify, even if they explicitly created a priority 0 deny rule locally?
That's sneaky.
It is. Something for you to mull over as you build your next secure cloud environment.